All right. Good evening. So, as promised, this is the completely asynchronous lecture for the midterm week. So this is going to be the November 1 through 5, 2021 week. And this would be lecture, I don't even know, like 13 or 14. It doesn't matter. Lecture for November 2nd / November 4th. Okay, so the idea again here is that you're going to watch this video on whichever day you're not rating the midterm. And then you would, after this video, you should have everything that you need to complete the fourth assignment, which is on confidence intervals and hypothesis tests. So that's lecture 7 and lecture 8. So lecture set number 8 is dedicated to the introduction of and examples of statistical hypothesis testing. So we're going to go through a fairly quick introduction to what hypothesis testing actually is and how it works. For the most part, it's a pretty straightforward process. We have an assumption checking step, and then we have 6 steps that we follow every single time we do a hypothesis test. Certain aspects of the steps are going to change depending on what it is we're interested in testing. But for the most part, if you just follow those 6 steps through, you should be able to arrive at the correct solution to the hypothesis test and an answer to the question that you are being posed. Oh, and then once we cover the steps of the hypothesis test and go through the examples, we'll also talk about errors in hypothesis testing. So basically quantifying what can go wrong each time you run the test. We're also going to talk a bit about using the t-table to find probabilities. We need this to find what is called the p-value, but I'll come back to that once we get to it. Okay, so the hypothesis test is the second type of statistical inferential procedure that we're learning about in this class. The first was the confidence interval. So you will recall that the confidence interval gives us 2 numbers that we believe the population mean, or rather that we are confident the population mean falls between. And to build the confidence interval, we use either a z-score or a t-value, and then we add and subtract our margin of error to the sample mean. And then from that, we make our little conclusion about what the interval actually represents. And this is done in 3 steps. And that's what we covered in lecture set 7. The hypothesis test, again, is also an inferential procedure. And actually, you can show that the solution to a hypothesis test and the corresponding confidence interval will give the same solution, but that's something we're going to talk about in the next lecture set. But the hypothesis test, unlike the confidence interval, is actually based around a question. So the interval is just our 2 numbers. Typically, we would just say we want to find the 95% confidence interval for mu, and then we would find the interval and we'd say here, like mu falls between these 2 values. The hypothesis test is actually formulated around a question. So the hypothesis test is built from the starting point of saying, what do we know about mu, which is the population mean? And in particular, we're going to ask 3 things about mu. Is mu less than some value? Is mu greater than some value? Or is mu different from some value? So we have one of the 3 different types of questions that we can answer with a hypothesis test: greater than, less than, or different from. Once we've formulated the question, we re-express the question through the null and the alternative hypothesis. So the null hypothesis is basically what we believe the true value of mu is equal to. So the null hypothesis will typically be something like mu equals 14. Okay, so the belief going into the question is that mu is equal to 14. The alternative hypothesis represents what we are asking. So if we want to know, is mu greater than 14, our alternative hypothesis would literally state mu greater than 14. If we were asked, is mu less than 14, our alternative hypothesis would just state mu less than 14, right? So the alternative expresses the question of interest, The null hypothesis simply states what we already believe to be true about the population mean. Okay, so as I had mentioned before, our hypothesis test is conducted in 6 steps. So technically, before the first step, you would declare a question or you would be asked some question, right? So on the assignments, for example, you're going to be asked, is the population mean greater than this number? Is the population mean less than this number? Is the population mean different from some number? Those will be the 3 basic questions that you can be asked, and you'll be asked those in a variety of ways depending on the context of the problem. So depending on the variable that you're working with, and I'll show you some examples of that in a little bit. Okay, so once you have your question set up, the first thing that we actually do is check the assumptions. And the assumptions of the hypothesis test are exactly the same as the assumptions of the confidence intervals we studied last class. So we require that a simple random sample was collected. We require that X bar is approximately normally distributed or normally distributed. And then we either have sigma or we do not have sigma. If we have sigma, our test statistic on step 3 is a Z-score, and then everything following step 3 uses the standard normal table. If we do not have sigma, our test statistic on step 3 is a t-value, and then everything that follows step 3 would then use the student's t-table, right? So there's a very strong connection between how we set up the interval and how we set up the hypothesis test, in that we check the same 3 things, and the absence or presence of sigma, which again is the population standard deviation, plays the same role with the hypothesis test that it did with the confidence interval. Okay, but explicitly, step 1, we state the null and the alternative. There are 3 different null and alternative hypotheses that we will consider. I'm going to go through what those are momentarily. Step 2, we state the significance level, which is called alpha. This will be given to you. So the same way that the confidence level is given to you in the question, the significance level will be given to you in the question. So it'll say test, that mu is greater than 14 at a 5% significance level. So that means that alpha is going to be 0.05, which is just the percent as a decimal. Step 3, we calculate the test statistic. You'll notice that our test statistics are just standardized and studentized X bar values. So these are values that we've actually seen in lecture set number 6 when we studied central limit theorem and sampling distributions. Step 4, on step 4, we basically decide, we use our test statistic to determine if there's evidence to reject or not reject the null. So this can be done in 2 ways. We either find a critical value or we find a p-value. You don't have to do both. You only have to do either critical value or p-value. Unless the question specifically states which one to do, you have a choice. They will give the exact same answer, so they will always agree. In the examples that I work through, I will do both of them so that you have illustrations of both. But again, you don't have to do both. Once you complete step 4, you then make a decision about H naught. So you decide if you're going to reject or not reject H naught, which is based off step 4. And then on step 6, you interpret the result of the test. So basically assumption check, step 1 through 6. That's how the hypothesis test works. All right. So as I mentioned, there's 3 types of hypotheses, or there's 3 sets of null and alternative hypotheses. For simplification, in this class, we always use the null hypothesis, H0 mu equals some value. So in every case, the null hypothesis is always going to be H naught, which is this here. So H naught, like H0, H naught, HO, you can call it whatever you want. HO, the population mean equals some number. That will be the same regardless of the question. The alternative hypothesis will change depending on what you're asking. So if you're asked, is there evidence that the population mean is different from 14? That means that the alternative hypothesis has a does not equal sign. So this is the different from value. Okay, so we use the does not equal sign when we're asked if something is different from or not equal to a quantity. This is the greater than sign. Okay, so in this case, we would be asked, is there evidence that mu exceeds, mu is bigger than, mu is greater than some value? So this would be the upper tail test. I'll show you why it's called upper tail momentarily. And then the other type of test is the lower tail test. So here we would have less than. So is there evidence that mu is less than some value, mu is smaller than some value? In that case, we would use the lower tail test. Okay, so we have 3 questions. Is mu different from a number? Is mu bigger than a number? Is mu smaller than a number? And our alternative hypothesis changes depending on which question we're trying to answer. So if mu is different from some number, that's a 2-tailed test, which means that we have the does not equal sign. If mu is greater than some number, that means that we have an upper tail test. So that is the greater than sign. And if mu is smaller than some number, that's a lower tail test. And that means mu is less than some number. And I'll go over what the upper and lower tail tests mean momentarily. Note that upper and lower tail tests are also called one-tailed tests. And that explanation will make more sense once I explain the upper and lower tail thing as well. All right, step 2 is very straightforward. We just state the significance level. So some professors don't even write this as a separate step. They'll just have step 1, H0, HA, and alpha. So they'll do it all at once. I write it as a separate step. It doesn't matter if you write it as part of the first step or if you do it separately, it's up to you. The point is, somewhere in the test, you have to declare what alpha is. So alpha is our significance level. It's also the size of the rejection region. More on that in a little bit. And it is a value that is given to you in almost every situation. If alpha isn't given to you, you can just assume it's equal to 0.05. So if alpha is not given, assume it is equal to 0.05. Okay. Okay, step 3, calculate the test statistic. So on step 3, we're literally just finding a z-score or a t-value. So if sigma is known, we're going to use the z-score, which is given by equation 1. If sigma is not known, we're going to use a t-value, which is given by equation 2. But you can see in both cases that the calculation of the value is pretty much the exact same thing. You take x bar, you subtract the theoretical mean, which is the value given in the null hypothesis, and then you divide by the standard deviation that you have over the square root of n. All right. Okay, step 4 tends to be the most complicated and difficult step of the hypothesis testing procedure. There, again, are 2 ways that we can perform step 4. So we can take what is called the critical value approach, or we can take what is called the p-value approach. Again, these are not joint. You can do one or the other. You do not have to do both. It's good to practice both and be comfortable with both, but you do not have to do both. I can't stress that enough. For the critical value approach, basically what we do is we look up a z-score or a t-value that depends on the type of test and the significance level. So the critical value is found based off of the null and alternative hypotheses and the significance level. The critical value is either a z-score or a t-value, and that depends on whether or not we know sigma or we do not know sigma. Once we have the critical value, we compare the test statistic to this value and then make a decision about H naught. So basically the idea is the critical value bounds what is called the rejection region. If the test statistic is inside the rejection region, you reject H naught. This concept will make more sense once we work through examples, but that's the general idea, is you can just think of the critical value as standing at the door or the gate to the rejection region, and the test statistic is either going to get inside that region or it's going to be outside that region. Okay. So as I had just said, the critical value is essentially a boundary between the region where we would decide to reject and the region that we would not reject. The rejection regions, or the critical values, are of 3 different types, and they depend on the alternative hypothesis. So basically what I'm saying is it's very important that we get the alternative hypothesis correct, because if we do not, we risk putting the rejection region in the wrong place. And if we put the rejection region in the wrong place, then we could very easily make the wrong decision about H naught. Okay, so it's very important that we get the rejection region properly set up. And again, that means that it's very important that we get the alternative hypothesis properly set up. Okay, so as I had mentioned before, there are 3 types of rejection regions, and they depend on the type of test. So basically, in the lower tail test, or the less than test, the reason it's called a lower tail test is because the rejection region is in the lower tail of the curve. Okay, so these here are normal or students T curves. For illustrative purposes, it doesn't really matter if it's normal or student T, because they're both bell curves centered at 0. But when we actually learn how to find the critical values, it does matter if it's normal or student T, because that basically indicates which table we're going to use. So we're not going to want to use the student's T table if we're using a normal test, though there is a trick that I'll show you from the student's T table depending on the significance level, but I'll come back to that in a little bit. Okay, so for the lower tail test, the reason it's called a lower tail test is because the critical value bounds the rejection region, which is in the lower tail. So when we have a less than sign in the alternative, that means that our critical value, which is going to basically just be a boundary between the rejection region and the non-rejection region, is a value that sits along the horizontal axis. So it's either a student T value or a Z score. So this is a Z score or T value, depending on the type, depending on if sigma is known or not. And it simply bounds 2 parts of the curve. So this red shaded part under the curve, this would be called the rejection region. So the rejection region is an area underneath either a student's T curve or a normal curve. And then this white unshaded part here, this would just be the non-rejection region. And now all we have to do is take our test statistic and determine where it falls. Does it get into the red part or does it stay in the white part? And all you do is just place where it would fall on the axis, right? So the axis is a Z or a T value, and we're just checking to see where the test statistic falls on the axis relative to the critical value. Okay, we'll do the upper tail test next. The upper tail test is just the reverse of the lower tail test. So now we're going to have a critical value in the upper tail. So this is Z or T. And as a result, the rejection region is now in the upper tail. So this again is our rejection region, and this white unshaded part is the non-rejection region. Right? Okay, so the tricky part with hypothesis testing is dealing with the does not equal sign, because what the does not equal sign does is it splits the area into each tail. So in this case, we're going to have 2 critical values. We'll have a critical value here, and we'll have a critical value here. Okay, so this will be a Z or a T, and this will be a Z or a T as well. And now you can reject in the upper tail of the curve, or you can reject in the lower tail of the curve. Okay, so now everything in the middle, that would be the non-rejection region. And if you get too far into either tail, you can reject. So that's why this is called a two-tailed test, because you have rejection regions in each tail. So the description of the test, lower-tailed, upper-tailed, two-tailed, that's just describing where the rejection region is located for that type of test. And again, the alternative hypothesis determines where the region is going to be located. So the less than sign means lower tail, greater than sign means upper tail, does not equal sign means two-tailed. All right, so basically to summarize what's given on the slide, if the test statistic gets into the rejection region, you reject H naught. Or from a rule point of view, from a rule-based point of view, it depends on the kind of test you're running, whether or not you get into the rejection region. So if you're running a lower tail test, the test statistic would have to be less than the critical value to reject. If you're running an upper tail test, the test statistic would have to be bigger than the critical value to reject. If you're running a two-tail test, you can either be smaller than the lower critical value or bigger than the upper critical value. So that would mean that the absolute value of the test statistic must be bigger than the absolute value of the critical value. Okay, so in that situation, you would reject for the two-tailed test. And that's true in both the T and the standard normal cases. And again, once we see illustrations, this will make more sense, but really it's just a comparison of two numbers. If this number, one number dictates where the rejection region is, if the other number gets into the rejection region, you reject. Okay. Now, the p-value approach tends to be the approach that students don't like. I think it's because they don't like finding probabilities, specifically with the student's t-table. They find that very hard. It's understandable because finding critical values with the student's t-table is very straightforward. You just go degree of freedom to significance level, and then there's your value. Finding probabilities is not quite as straightforward, especially because they're not whole numbers anymore. They're built on ranges. But I'm going to go through some examples of that later. Okay, so what is a p-value? Basically, it's a probability of getting a test statistic as extreme as the one you observed, assuming the null is true. What does that mean in a more plain English? Basically, the p-value is a measure of how likely it is to observe the null hypothesis that we are working with. So if the p-value is very small, that would mean that the null hypothesis is unlikely, so we would reject the null. If the p-value is very big, that would mean that the null hypothesis is very likely, and therefore we would not reject it. Now, what does it mean to be small or big? We're talking about a probability. So the number is naturally bounded between 0 and 1 or 0 and 100%. So what is a small p-value? What is a big p-value? Okay, well, as you'll see momentarily, the size of the p-value is actually determined by comparison to the significance level. So with both the critical value approach and the p-value approach, it is the size of both the critical value approach and the p-value approach use comparison of two numbers. So in the critical value approach, we compare a test statistic to the critical value. In the p-value approach, we compare our p-value to the significance level. Okay, the p-values are set up in the exact same way as the critical values, except that they're based off a test statistic. So for a lower tail test, where we have the less than sign, we would now mark down our test statistic on the axis. And the p-value is just the area below that test statistic under the curve, right? So hopefully what you're noticing here is that we're using a lot of the techniques that we studied in lecture set number 5. Like we're finding area underneath a standard normal curve, or we're finding a value based off an area under the standard normal curve. And then we're doing that same thing with the t-table. So we're just taking the techniques that we had learned in lecture set 5, and now we're using them in an actual application. Okay, for the upper tail test, same basic relationship. So here's our test statistic. And now the p-value is going to be this area here. Okay, and then in the two-tail case, this is where it gets a little bit tricky. So now you consider the positive and the negative of your test statistic. Right, and then up here, we'll do the positive test statistic. And now the p-value is the area in both tails. Okay. But for the most part, these are found in the same way as the critical values. It's just that instead of using the significance level to find the critical value, we use the test statistic to find the p-value, but it's the same style of technique. We're just using a different value. And I'm going to give you lots of illustrations of this for both normal and student t curves. But this is just the general idea of how it works. All right. So I had mentioned that when the p-value is small, we would reject null hypothesis. When the p-value is big, we would not reject the null. Okay, well, how does this actually work? Well, we take the significance level for the test, which is declared at this in step 2. And we say if the p-value is less than or equal to the significance level, it's small enough to warrant rejection. And then we say the opposite. If the p-value is bigger than the significance level, then we do not reject. So it's only one rule for every type of test. The critical value is technically a larger set of rules because it depends on the alternative, how we use the critical value. But with the p-value, it's always the same thing. If p-value less than or equal to alpha, reject the null. And that's true in every situation, regardless of the type of test. Okay, as I had mentioned before, the hypothesis test is an assumption check, same assumptions as with the confidence intervals. Then it's a 6-step procedure. On step 4, we can take either the critical value or the p-value approach. They do the exact same thing and they serve the exact same purpose. We do not have to do both, but I will demonstrate both so that you have illustrations of both. All right. When sigma is known, the assumptions of the test are given here. So we collected a simple random sample, and the variable of interest is normally distributed, or the sample size is large enough that the CLT takes over. When sigma is unknown, we have the simple random sample calculation, and then we have the same assumption on the variable, so that we either sampled from a normal distribution or sample size is technically large enough. But typically for the students T, we just focus on evidence that we sampled from the normal, but we won't go into a lot of detail about why. So same set as with confidence intervals. Okay, so SRS, normality, and then do we have sigma or do we not? If we have sigma, use a Z-score. If we do not, use a t-value. Okay, so we're going to work through some exercises now so that we can get a grasp of this. Exercise number 1. The National Funeral Directors Association reported that the average cost of a full service funeral in 2005 was $6,500 or $6,500. A simple random sample of 36 funeral homes gave X bar equals $6,819. If sigma is equal to $1,265, test the claim that the true mean is not equal to $6,500 at the 5% significance level. Okay, so we have a lot of information in this question. First, we have an SRS of 36 funeral homes. So this is sample size 36, and it's telling us that we have a simple random sample. Okay, then we have X bar, we have sigma, and then we're told test true mean is not equal to 6,500. So this is telling us to test that mu is different from 6,500, 5% significance level. All right, so we have everything that we need. We'll start by writing out the assumptions. So 1 SRS, this is clearly good because we're told we have an SRS. 2 normality, this is good by CLT since the sample size is greater than 30. So we have a sample size of 36, which means that the central limit theorem would take over. So X bar is going to be approximately normally distributed by the central limit theorem. So we can check off the second assumption. And then on 3, we have sigma known. This is also true. So we're told that sigma is equal to 1,265. Okay, so step 1, we're going to write out the null and the alternative hypothesis. So the null hypothesis is always mu equals the theoretical value, which in this case is 6,500. So we're asked, test the claim that the true mean is not equal to 6,500. So that's basically saying mu 0 is 6,500 in this example. Okay, we want to test that it's not equal to. So that means that the alternative is going to be HA mu does not equal 6,500. So is not equal to is being represented here. Okay. On step 2, we declare the significance level. We're told to test at the 5% significance level. So alpha is 0.05. Okay, on step 3, we compute our test statistic. So since sigma is known, we're going to have X bar minus mu 0 divided by sigma over the square root of n. So this is going to be 6,819 minus 6,500 divided by 1,265 divided by the square root of 36, which is 1.51. Okay, now on step 4, we can take either the critical value approach or we can take the p-value approach. Okay. I'm gonna just give myself a little more room here. Okay, so the way that this works, we start by sketching out a normal curve. So we have a z-score as the test statistic. So that means that we're going to be working with a standard normal table and the standard normal curve. Okay, so here's my sketch of a standard normal curve. We're running a double-sided test. So we have HA, mu is different from 0. So that means that we're going to have a critical value in the upper tail and a critical value in the lower tail. Okay. Now, the red shaded part here, this is going to be a size of alpha over 2. So when we run a two-tailed test, the critical value or the significance level gets split in half. So this is going to be a size of 0.025, and this is going to be size 0.025. When we have a one-sided test, we put all of the area in that upper or lower tail. So we do not divide by 2 in the one-sided tests, only in two-sided tests. Okay, so that means that this value here is the z-score with 0.025 in the upper tail. And this value here would actually just be the same number as the upper critical value, but a negative. So this would be negative z 0.025. So these two values are the same. It's just that one is negative and one is positive, but they're the same value. All right. So what does that mean? It just means that all we have to do now is go to our normal table and figure out what z-score puts 0.025 in the upper tail or what z-score puts 0.025 in the lower tail. Okay, so if we want to use the normal table, we can just go to the negative side. We can look for 0.025 inside the table. That's right here. All right, and then we go out to the axes. So that gives us negative 1.906. Okay, so the critical value for this test is negative 1.96 in the lower tail, positive 1.96 in the upper tail. Right. Now, I mentioned before that there's a trick. If you go to this student T table and you go to page 2 and you scroll to the bottom, this actually gives you Z scores for specific significance levels. So you'll see here, we have Z subscript 0.025, which is 1.96. So this would be another way that we could get that value quite quickly. Okay, now we take our test statistic. So our test statistic is equal to 1.51, and we place it on the axis to determine where it falls. So in the middle of the graph, I have 0. The upper critical value is 1.96. So that means that the test statistic would be roughly here. So this is going to be Z equals 1.51. We don't need to draw it exactly where it's going to be, but the point is that it doesn't get into the rejection region because it's between 0 and 1.96. So it's outside the rejection region. So based off the critical value approach, we would not reject. Okay, so that's the first way of doing step 4. The second way is to use the p-value approach. Again, you don't have to do both. You only need to do one. I'm just showing both for illustration. Okay. So with the p-value, we have a test statistic that's a z-score. So we draw our standard normal curve. Now what we do is we mark down where our test statistic is. So let's say right about here. So this is z equals 1.51. It's a two-tailed test. So we also mark down the positive or the negative. So we just say negative z equals negative 1.51. And we're only doing this because it's a two-tailed test. Okay, so now our p-value is the area to the right of positive 1.51 and the area to the left of negative 1.51. Okay, so the p-value is equal to the probability that z is less than negative 1.51 plus the probability that z is greater than 1.51. Because the standard normal table is a symmetric table, this is equivalent to 2 times the probability that z is less than negative 1.51. It's also equivalent to 2 times the probability that z is bigger than 1.51. Okay, so now we just go to our normal table. We look up negative 1.51, which is right here. Okay, so the probability that z is less than negative 1.51 is 0.0655. So we have 0.0655. And therefore the p-value is 0.1310. Okay, on step 5, we make a decision about whether to reject or not reject H naught. So if we use the critical value approach, okay, we would say since test statistic is not in rejection region, do not reject H0. If we took the p-value approach, we would say since p-value is greater than alpha, do not reject H0. And that's pretty much it. The last part, we just have to summarize our findings. So the conclusion of a hypothesis test is always basically state the significance level, state the result in the context of the null hypothesis. So we always state our result in the context of the null. Or sorry, state in the context of the alternative. My bad. So we're going to have at the 5% significance level. And effectively, every conclusion is going to start this way. We're going to say at whatever significance level we're at. The data do not provide. Okay, so now what we're doing is we're stating what the data have shown us in the context of the alternative. So we did not reject the null. So that means that the data do not provide evidence that the alternative might be true. So what I'm saying right now is, or what I'm writing right now is that the data do not provide evidence that the alternative is true. So at the 5% significance level, the data do not provide sufficient evidence to suggest that the average cost of full service funerals is different from 6,500. Okay, so I have at the 5% significance level, the data do not provide. So I have do not provide because I'm not rejecting the null. So do not provide sufficient evidence to suggest that the average cost of full service funerals. So this is what we're measuring. We're measuring the cost of full service funerals, and we're talking about the average value. Okay, so they do not provide sufficient evidence to suggest that the average cost of full service funerals is different from 6,500 because our alternative was different from or not equal to. Okay, so example 2, suppose that student debt for all second-year students at the U of A is normally distributed with mu equals 1,700 and sigma equals 330. If a simple random sample of 15 students had an average debt of $1,600, is there sufficient evidence to conclude that the average debt for all second years is less than $1,700 at the 10% significance level? Okay, so lots of information here. So we have normally distributed. So student debt is normally distributed. So that's what we're measuring here is student debt. The average is 1,700. The standard deviation is 330. We have a simple random sample of 15 students, and that simple random sample had an average debt of 1,600. So X bar is 1,600 in this case. Is there sufficient evidence to conclude that the average debt is less than 1,700 at the 10% significance level? Okay, so we start off with our assumptions. Okay, so number 1, SRS. So this is true. We're told that we have an SRS. Number 2, normality. This is true because we're told that student debt is normally distributed. And then number 3, sigma known. This is true because we're told sigma is equal to 330. Okay, on step 1, we're going to have H0 mu equals 1,700. Okay, so notice that I'm still using mu equals some number in my null. It doesn't matter what the alternative is. This is always going to be the null that we use. Okay, we're asked if student debt is less than 1,700. So we're going to have HA mu less than 1,700. On step 2, we're going to declare our significance level. So that's alpha equals 0.1 because we're told the significance level is 10%. Okay, so then on step 3, we compute our test statistic. So we have Z equals X bar minus mu 0 over sigma divided by the square root of n. Again, we're using a Z score because sigma is known. So now we have 1,600 minus 1,700 divided by 330 over the square root of 15. That is 1.17. All right, on step 4, we can take either the critical value approach or we can take the p-value approach. If we take the critical value approach, we start by sketching out our normal curve. This is a lower tail test. So now we're going to have a negative critical value. Okay. Because it's a lower tail test, it's a one-tailed test. So that means that all of the information is in one tail. So this thing here is size alpha, which is 0.1. So this is negative Z 0.1. All right. Okay, so to find this value, we can go to the normal table. We can look up 0.1. So the closest we can get to 0.1 is 0.1003. So that gives us a critical value of negative 1.28. Okay, so negative 1.28. If we go to the student T table, page 2, you can see that we have Z 0.1 here, 1.282. So we can use negative 1.28 or negative 1.282. It doesn't matter, it's going to give the same result. Okay, so we'll use negative 1.28. Okay, it's a one-tail test, so we only have to worry about the lower tail. Now we're going to take our test statistic, which is, negative 1.17. 1,600 minus 1,700 is negative 100, right? And then we're going to see where does this thing fall. Okay, so if the boundary is negative 1.28, 0 is in the middle, that means that our Z score is at negative 1.17, which is right here. Probably a little bit further over, but again, we don't have to be exact. Okay, so this again would mean we do not reject. If we take the p-value approach, okay, so here's 0. Here is Z equals negative 1.17. So now we're working with the test statistic. It's a lower tail test. So this green shaded part here is the p-value. Since it's a one-tail test, we're only interested in the lower tail. So we're only going to take that lower tail of information. Okay. So that means that the p-value is equal to the p-value is equal to the probability Z is less than negative 1.17. Okay, so now we're going to look up negative 1.17. Which is 0.210. Or 0.1210. Okay, so our p-value here is 0.1210. Okay, so then on step 5, same idea as before. So if we take the critical value approach, the test statistic is not in the rejection region. So therefore we do not reject H0. And if we take the p-value approach, since the p-value is bigger than alpha, we do not reject H0. All right. And then on step 6, we would say at the 10% significance level, the data do not provide sufficient evidence to suggest that the average student debt of second year U of A students is less than $1,600. Okay, so you can see for the conclusion, same general setup as before. So at the 10% significance level, the data do not provide sufficient evidence to suggest that the average student debt. So now I'm just talking about the variable in this problem. A lot of the setup is the same at the whatever significance level, the data do or do not provide. If we do not reject, they do not provide. If we do reject, it does provide. Do not provide sufficient evidence to suggest that the average student debt, which is what we're measuring here, is less than 1,600, the proclaimed alternative. Okay. When we are running a hypothesis test using the student's t-table, the steps are exactly the same. The only difference is that sigma is unknown. Now, in terms of finding critical values and p-values, this makes a big difference because we're not using the standard normal table anymore. We're now using the student's t-table. We know how to find critical values using the student's t-table because we learned how to do it for confidence intervals. What we haven't done is learn how to find probabilities using the student t-table, which tends to be a very difficult unit for students because these are no longer exact values, except for in very particular situations. Most often the p-value is a range. So it's built around like a greater than or a less than symbol. So before we go through the hypothesis tests that show the student T examples, I want to go over finding area underneath the student's T curve. So here is an example of how this would work. So suppose that we wanted to find the probability that T was bigger than 1.96 when N is equal to 14. Okay, the first thing we do is we find our degrees of freedom. So that's 13. Okay. So remember, degree of freedom is equal to N minus 1. So we have 14 observations. So the degrees of freedom is N minus 1, which is 14 minus 1. Okay, now what we do is we basically scroll across the degree of freedom line and we look for where 1.96 would fall into. Okay, so we have 1.350, we're bigger than that. We have 1.771, we're bigger than that. 2.160, we're smaller than this. Okay, so we're going to be here between this quantity and this quantity. Okay, so it's very important that you don't round. So we can't round to the closest value anymore. We simply determine where our value would fall based off of the numbers that are given to us. So 1.96 is between 1.771 and 2.160 when the degree of freedom is 13. Okay, so that means that the area of interest is going to be between the two tail probabilities that are shown here. So you can see here in the graph, I've highlighted what we're looking for. So this is the probability that t is greater than 1.96. So just like before, this value here is our boundary value, so 1.96. What we're trying to find is this red shaded part here, so this area underneath the curve. What we are showing is that this red shaded part here is going to be between 0.05 and 0.025 because we can't round to the closest value. Since 1.96 is between 1.771 and 2.160, our area of interest is between 0.05 and 0.0025. Okay, so in conclusion, we would write the probability that t is bigger than 1.96 is between 0.025 and 0.05. Okay, let's look at a few examples. So example 1. What is the probability that t is bigger than 2.650 when n equals 14? Okay, so just like with any of these problems, we start by sketching out a curve. So this is our student t curve. Our student t value is 2.650. We want to know what is the size of this red shaded part here. So this red shaded part here is the probability that t exceeds 2.650. Okay. All right, so our degree of freedom is equal to n minus 1, which is equal to 13. So we go to our student t table. We highlight 13 degrees of freedom. Our value of interest is 2.650. Okay, so we start here. 1.350. 2.650 is bigger than that. Move to the next value. 1.771. 2.650 is bigger than that. Move to the next value. 2.160. 2.650 is bigger than that. 2.650. Okay, so this is a rare case where our value is exactly equal to a number in the table. So that means that the area of interest is exactly equal to this tail value. So you can see that the way the t table works is that inside the table, we have our critical values. The critical values are these values here. These little tail values up here are the size of the area in the upper tail. So because we are exactly equal to 2.65, that means the probability that a t value is bigger than 2.65 is equal to 0.01 when n is equal to, or when the degree of freedom is equal to 13. Okay, so here we have 0.01. Okay, so that's the conclusion or the solution to this problem. Question 2, same idea. So this is my really good student t curve. Okay, so here's 2.451. We want to know the probability that t is bigger than 2.451 when n is equal to 21. So we have df is n minus 1, which is 20. We're looking for this red shaded part here. All right, so we go to our student t table. We have 20 degrees of freedom. Our value is 2.451. So we scroll across the line. 2.451 is bigger than 1.325. 2.451 is bigger than 1.772. 2.451 is bigger than 2.086. 2.451 is smaller than 2.582. Okay, so we are in between these two numbers here. Okay, so then we scroll to the top, and that means that our area of interest is between 0.01 and 0.025. So the size of the area that we're looking for is between 0.025 and 0.01. Okay, so we would say therefore, therefore 0.01 is less than the probability that t is bigger than 2.451 is less than 0.025. So the reason that we had to go through these two exercises is because this is exactly the technique that we're going to use to find p-values. So every time we have to do a student t-test and we want to find a p-value, this is how we're going to do it. So let's take a look at that now. A manufacturer produces bolts that are supposed to have a weight of 2.50 grams. A simple random sample of 20 bolts yielded X bar equals 2.53 grams and little s equals 0.04 grams. Test whether the population mean weight is different from 2.50 at alpha equals 0.101. Assume bolt weight is normally distributed. Okay, so a lot of information here. We have SRS of 20 bolts. We have X bar 2.53, S 0.04. Test population mean different from 2.50 at alpha 0.01. Bolt weight normally distributed. Okay, so we start off with the assumptions. So we have SRS. So this is good. We're told it's an SRS. 2, normality. This is good. We're told bolt weight is normally distributed. 3, sigma, known. Okay, this is clearly not good because we're given sample standard deviation, not sigma. So, okay, so all that means is that we're going to use a t-value rather than a z-score. So on step 1, we have H0 mu equals 2.5 versus HA mu does not equal 2.5, right? Because we're asked to test if it's different from, not equal to. Step 2, we have alpha equals 0.01. That's given to us in the problem. Step 3, we have t equals x bar minus mu 0 divided by s over the square root of n. So that's 2.53 minus 2.50 divided by 0.04 over the square root of 20. And that's 3.354. All right, step 4. So we take either the critical value or the p-value. Don't have to do both. I'm going to show you both. So if we do the critical value, we sketch out our student t-curve. Okay. So it's a double-sided test. We have a does not equal sign in the alternative. Okay, so we're going to have a critical value in the lower and the upper tail. So again, when we do the two-sided test, we split the area equally into each tail. So this is size alpha over 2, which is 0.005. And this is also going to be size 0.005. Okay, so this critical value is a t-value on 0.005, and we have a sample size of 20, so that means 19 degrees of freedom. because the degree of freedom is n minus 1. Okay, so that means in the lower tail, we're just going to have the negative 0.005, comma 19. All right, so to find the critical value, we go to our student t table, and all we're going to do here is match t 0.05 to the degree of freedom, which is 19. That gives us a critical value of 2.861. So the critical value for this test is a t value at 0.005 and 19, which is 2.861. So we have 2.861, negative 2.861. Then we take our test statistic, which is 3.354. You can see that this test statistic gets inside the rejection region on the upper tail. So 3.354 is bigger than 2.861. So therefore, we are inside the rejection region. So we would reject on the next step. Okay, if we take the p-value approach, we start by sketching out our t-curve. So centered at 0. Now we actually mark down our test statistic, and we also consider the negative of our test statistic. So our p-value here is going to be the probability that t is bigger than 3.354 and the probability that t is less than negative 3.354. So the p-value is equal to the probability t is less than negative 3.354 plus the probability t is bigger than 3.354. Okay, again, the curve is symmetric, so those two green parts are the exact same size. So this is 2 times the probability that t is bigger than 3.354. Okay, now what we're going to do is figure out what is the probability that t is bigger than 3.354 when the degree of freedom is 19. So we go to our t table. We have 19 degrees of freedom, and our test statistic is 3.354. So we scroll across the line. 3.354 is bigger than 1.328. 3.354 is bigger than 1.729. 3.354 is bigger than 2.093. 3.354 is bigger than 2.539. And 3.354 is bigger than 2.861. So now we're over here. So we are bigger than this value. Okay, so we scroll up to the top. We only have one tail area, which is 0.005. So what we would say here is, since our test statistic 3.354 is bigger than 2.861, which is the largest listed value, our tail area must be less than 0.005. So what we have determined is that this here is a size that's smaller than 0.005. This here is a size that's smaller than 0.005. So if both areas are smaller than 0.005, then the p-value must be less than 0.01. We're just going to add those two bounds together. So we would say, since the probability that t is bigger than 3.354 is less than 0.005, then the p-value is less than 0.01. Okay, so I've just added 0.005 to itself to get 0.01. So now my statement here is the p-value is smaller than 0.01. Okay, so that takes us to step 5. So from the critical value approach, we would reject H0 since test statistic in rejection region. And from the p-value approach, we would reject H0 since the p-value is less than alpha. So the p-value is less than 0.01. Alpha is 0.01. Therefore, the p-value is less than alpha. Okay, and then on step 6, we would say at the 1% significance level, the data provide sufficient evidence to suggest that that the average bolt weight for this population is different from 2.50 grams. Okay, so I have here at the 1% significance level, the data provides sufficient evidence to suggest that average bolt weight for this population is different from 2.50 grams. Okay. Experimental determinations of spring constants were made for 3 types of springs: type 1, type 2, type 3. At the 5% significance level, is there evidence that the long run mean for type 1 springs is greater than 1.86? Use the table below. All right, so we want to test if the long run mean is greater than 1.86, and we're using these values shown below. Okay, so assumptions. So we have 1 SRS, 2 normality, 3 sigma known. All right. We don't know, and no. So what do we do? Well, in this situation, for the purposes of this class, what we would do is we would finish the problem. When we get to step 6, which is the conclusion, we would then acknowledge that the assumptions need to be checked. So in this situation, because we don't have the assumptions, we're going to make a statement in the conclusion saying we need to verify these assumptions in order for this result to be likely. Okay, so step 1, we're going to have H0 mu equals 1.86 versus the alternative that mu is greater than 1.86, right? So here we have greater than 1.86. Step 2, we're going to have alpha equals 0.05. Okay, so you can see here we have 5% significance level. So alpha 0.05. Step 3, we have t equals x bar minus mu 0 over s divided by the square root of n. So this is 2.03 minus 1.86 divided by 0.068 over the square root of 8. And this is 7.071. All right, so now if we take the critical value approach, okay, we're going to start by sketching out our student t-curve. This is an upper tail test. So we're going to have all of the area in the upper tail. So this is going to be a size 0.05. So this is a t on 0.05 and 7 because we have 8 observations. So the degrees of freedom is 8 minus 1, which is 7. We go to our t-table. We match 0.05 to 7. That gives us 1.895. So the critical value for this test is the t-value on 7 degrees of freedom and 0.05 upper tail area, 1.895. Okay, then we take our test statistic. We can see that this is much bigger than the critical value. So the test statistic is well inside the rejection region, so we can reject here. All right, if we take the p-value approach, we can sketch our area here. So here we're going to mark down our test statistic. Okay, so our p-value is this green shaded part here. So this is the p-value. So we have the p-value is the probability t is bigger than 7.071. And this is on 7 degrees of freedom. So we go to our t-table. We look up 7 degrees of freedom. And our t-value is going to be here. Right? So you can see that 7.071 is bigger than any of the values listed on the line. So that means that our tail area is going to be smaller than 0.005. So in this case, we would say, since the probability that t is bigger than 7.071 is less than 0.005, then the p-value is less than 0.005. Okay. Okay, so then on step 5, regardless of the approach we take, we can see that we're going to reject. If we use the critical value approach, we're rejecting because the test statistic is in the rejection region. If we use the p-value approach, we're rejecting because the p-value is smaller than 0.005. Therefore, it has to be smaller than 0.05. So here we would reject H0. Okay, so then on step 6, we would say if the assumptions of the test can be verified, then the data provide sufficient evidence to suggest that the mean TSC of type 1 springs is greater than 1.86 at the 5% significance level, right? So I went a little out of order this time because I put my significance level last, but it doesn't matter as long as we include it in the statement. So what we found here is if we can verify those two assumptions, then we have evidence that the mean TSC of type 1 springs is larger than 1.86 at the 5% significance level. Any questions? Of course not, I'm alone. All right. So we have now seen 2 examples of hypothesis testing when sigma is known, and 2 examples of hypothesis testing when sigma is unknown. So that will be more than enough to complete what we need for the assignment. There are 2 other things, or 1 other topic that we need to discuss in this lecture set, which is errors in hypothesis testing. Note too that there's 2 other examples given at the end of this lecture set on hypothesis testing, which will also have solutions provided. Okay, so there are 2 major types of errors in hypothesis testing. There's rejecting the null hypothesis when the null hypothesis is actually true. This is a type 1 error. And there is failing to reject the null hypothesis when the null hypothesis is actually false. And this is called a type 2 error. So these are the 2 major types of error in hypothesis testing. Rejection when you should not, failing to reject when you should. That's effectively what these 2 errors are. Okay. So we can actually calculate the probability of each of these errors. And what's interesting is that our probability of type 1 error is equal to alpha, which is the significance level. So we actually declare an acceptable type 1 error amount at the start of the problem. So we actually start off by saying the type 1 error equals alpha, which is the significance level. The probability of a type 2 error we call beta. And we can calculate this, but this is not something that we're going to do in this class. Alpha and beta are not complements. So alpha plus beta does not equal 1. Alpha and beta have what we refer to as sort of a seesaw relationship. So if this is alpha here, and this is beta here, and this is a seesaw, or a teeter-totter, right? Then basically what happens is as one goes up, the other goes down, but they don't do it in a complementary way. They do it more in sort of like a parabolic way. So you can think of the shape of the 2 as being something like this. So it's sort of like a parabolic relationship, not complementary. Okay, so we're just going to work through a couple of examples that describe how these errors would work. Okay. So in this first illustration, I have at McEwen, students taking stats are known to be mentally tough. So you can tell that this is not at all a tailored example. A device called the Bryaноmeter measures mental toughness. So you can tell that this is not tailored and I'm not a giant nerd. Results show that the average score among this population is 45 Bryons. The majority of students believe the score is actually higher than 45. Okay, so we want to declare the null and alternative for this question. So here we have the belief that mu is equal to 45 versus the alternative that mu is bigger than 45. Okay, so in part B, we want to know what are the type 1 and type 2 errors. So the type 1 error would be rejecting H0 when in fact the average score of the population is 45 Bryons. So the type 1 error here would be we collect a sample, we conduct a hypothesis test, and we reject the null. But the truth is that the population actually is, or actually does have a mean of 45, but the sample didn't show that. So that would lead to a type 1 error. The type 2 error would be not rejecting H0 when in fact the average score of the population is greater than 45 Bryants. Okay, so the type 2 error would be we collect a sample, we do a hypothesis test, and we reject, we do not reject the null. Okay. So we say that there is evidence to suggest that the average score is greater than 45 Bryons. Wait, sorry. Yeah, so we would say that we would basically say there's no evidence to suggest that the average score is bigger than 45. So there's evidence to suggest that it's equal to, but in reality, the mean of this population actually is bigger than 45. All right. Okay, suppose that determining the average Bryan score exceeded 45 was crucial to the success of your test. Would you want beta to be small or would you want beta to be large? Okay, so beta is probability type 2 error, which is probability fail to reject given H naught is false. So we would want, if rejecting H naught was crucial to us, so if it's crucial that the average score is bigger than 45, that would mean that it's crucial that we reject the null. So therefore, we would want beta to be as small as possible because beta is the probability of not rejecting. Part B, explain the impact on the researcher if beta is equal to 0. Well, for our purposes, this is ideal because we will always reject. But the problem is you're always rejecting, so the probability that you make a type 1 error is now going to be higher since you have beta set to 0. Okay, so that brings us to the end of the section on hypothesis testing, so lecture set 8. I'm going to post this video as per usual on YouTube, and I suggest that you watch it on the day you're not taking the midterm, make some notes, and if you have any questions, you can either email me or come to office hours to ask them. And this is, of course, all the material you need to finish the 4th assignment as well, which is due the Tuesday after the break. Okay, so if you are seeing this lecture set and you haven't had the midterm yet, good luck on your midterm and have a nice reading week. If you're watching this and you had the midterm, I hope the midterm went well and have a nice reading week. And I will see you guys in a live session once we get back.